Last time we were talking about Floyd-Warshall algorithm. And we pretty much finished talking about that, but I wanted to make just one more comment because that material is not in your book, but I mentioned that you can, there's a very good discussion of it, a reasonable discussion of it at any rate, in Wikipedia. So you can see the details of that in Wikipedia, and that's fine. The one thing that I did object to in Wikipedia is they have the following statement. It says the Floyd-Warshall algorithm compares all possible paths through the graph between each pair of vertices. Okay, so we saw a dynamic programming solution to this problem of finding the shortest path between every pair of vertices, and they're roughly n squared pairs of vertices, and the algorithm runs in n cubed time. Okay. By dynamic programming. Now this statement from Wikipedia is that the Floyd-Warshall algorithm compares all possible paths to the graph between each pair of vertices. How many people would say that's a fair assessment of what the Floyd-Warshall algorithm does? Okay, how many people would say that's not a fair statement about what Floyd-Warshall algorithm does? Okay, and how many people wouldn't say anything? How many people haven't said anything yet? Okay, this is not good. We had 0 on my first question, 1 on the second question, and 1 on the third. Okay, but there's some 56 of you there. Everybody should have answered at least once. So how many people think this is a fair statement? How many people don't think it's a fair statement? Okay, 2 now, or 3, 4. And how many people haven't answered? Okay. Now how many people haven't answered? At any rate, there's still some of you out there. Okay. Brian, that's your name?
Yeah.
Why did you say it's not a fair statement?
Because it's not really comparing it's running through them separately.
Okay, the main point was that it's not really comparing. When you say it compares all of them, that implies it somehow explicitly looks at every path between every pair of nodes and evaluates its distance and then compares them and finds out which is the shortest and so on. Well, you can just do a few little examples to convince yourself that the number of paths, even between some fixed pair of points, is vastly larger, can be vastly larger than n cubed. The algorithm runs in n cubed time. If it's explicitly looking at every pair of paths or explicitly enumerating paths, there's no way it can run in n cubed time. And the whole point of dynamic programming, the spectacular success of dynamic programming, is that it can find the shortest path, not only between a fixed pair of nodes, but in fact in the Floyd-Warshall case, for every pair of nodes it finds the shortest path, or the distance anyway of the shortest path, by not explicitly enumerating paths, by doing something which is guaranteed to give you the optimal distance, the shortest path, but doesn't explicitly enumerate them. And so this, maybe if you parse this very, very carefully, you could say it's okay. Floyd-Warshall compares, but it depends on what you mean by compare. If it's an explicit comparison of all possible paths, that's wrong and misses completely the whole spirit and elegance and importance of dynamic programming. But you see this kind of statement all over the place. This isn't just from this Wikipedia, whoever wrote that article. You just see it again and again and again. It kind of makes you wonder whether the person understands what's really going on in dynamic programming and how powerful it is. And it's not just brute force enumeration. Now, the other 3 who had your hands up saying, no, this wasn't a fair statement, was that what you were going to say?
Yeah. I was also going to say, because you were asking a question, you wanted to ask the question.
Oh, yeah, well, that's, yeah, okay. Yeah. Right. Yeah, that's the trick answer, not the trick question. Yeah, right. Okay. All right, so that's all I'm going to say about that algorithm. We didn't do traceback, but that might be on your, that's a good question on your, for your homework perhaps. Okay, so today what I want to talk about is another topic that's also not in your book, but I have notes that I'll put up on the web for that. And this is a problem that relates to paths, not shortest paths per se, but paths in graphs, and shows how to solve a particular problem by casting it as a problem of a path in a graph and asking a question about the existence or non-existence of certain kinds of paths, and gives what I think is an amazing result, one that I found very surprising when I first learned about it. And so this is the problem that's called unique decipherability. Unique. Decipherability. And this is actually a problem that it came up in the 1940s and had some importance in coding theory for a very short time, and then for reasons that I won't explain, became unimportant in coding theory, but it still remains an interesting question in computer science and in algorithms. And so, without really talking about the coding theory basis of the problem, just think of it in the following way. You're given a set of strings, and that's called a code. Okay, so let me give you an example. So, for example, C could be ABA, BB, AB, and BA. Okay, so each one of these is a string. So this code has 1, 2, 3, 4, 5 strings. Each string is also sometimes called a code word. And what you're able to do is make messages by selecting code words and concatenating them. You can use a code word as many times as you like, so there's no limit on the length of the messages that you can create. So here's another example of a message. For example, ABA, ABB, ABB, BAAB. There's a message that can be made from this code because it uses code words, concatenates code words together to make a message. So, for example, ABA is a code word, ABB is a code word, ABB is a code word, BAAB, right? So that is a message. Okay. Now, just jumping ahead a little bit, can anybody see whether there's another way of writing this message as a concatenation of code words with different code words? I see a hand up. Yeah.
Yeah, the first code word can be broken up into A, B, and then A.
Yeah, so rather trivially, this one could be broken up into A, B, then followed by A, and there may be other ways of doing that. So already, just on this first little piece, we see that if you have this code and you receive this message, then you don't know whether the message was the ABA code word first, or whether it was code word AB first, then followed by code word A. So this message, this is an example of a message that is not uniquely decipherable. Of a message that is not uniquely decipherable. Or uniquely decipherable is just going to be abbreviated as UD. Okay? So getting messages that are not uniquely decipherable is not a good thing because there's ambiguity there. You don't know. On the other hand, if we use this message, A, B, B, A, B, well, how do we parse that? That's A, B, B, followed by A, B. And is there another way of parsing it? Well, the longest code word is 3, so there's no longer one than that. A shorter code word is AB, but, okay, so you could parse it AB, and then you have BAB as a way of doing that. Well, there's a way of doing BA, but then you're stuck because there's no B. So it looks like the bottom parse is the only way of parsing this particular message. Okay? So this is an example of a message that is uniquely decipherable. Notice that you don't determine this uniquely decipherable until you're at the very end. You're going along here and you're able to parse it A, B, B, A, and so on, but you get to the end and you realize that alternative parse isn't going to work. And this was the only parse. So this is uniquely decipherable. Okay? So we know what a code is, code words, messages. Some messages are not uniquely decipherable. Some messages are uniquely decipherable. Okay? So another definition, given a code, C, well, a code, actually I shouldn't say given, that a code C is called uniquely decipherable if and only if every message that can be created from C is uniquely decipherable. Okay? So that's the definition. That's a perfectly fine definition. I haven't stated a problem yet, although you can imagine what the next problem is. But, for example, is this code uniquely decipherable? No, it's not uniquely decipherable because we've already seen a message that it can be made from it that's not uniquely decipherable. And the definition says that a code will be called uniquely decipherable if and only if every message that can be created from it is uniquely decipherable. Okay, so now a problem. Given a code, determine if it is uniquely decipherable. And of course, when we say determine in this class, we mean come up with an algorithm that can always determine whether the code is uniquely decipherable. And, of course, we want something that's efficient. Now, if you take sort of the most brute force approach to trying to answer this question, you might think about generating all possible messages. You have a code, and you need to know whether every message that you can create from it is uniquely decipherable. So you could think of conceptually generating all those messages, and for each one testing if they're uniquely decipherable, although we don't even yet have an algorithm to test whether a message is uniquely decipherable. But imagining we did have an algorithm that could test whether a message is uniquely decipherable, what's wrong with that conceptual approach? Yeah. Hold on a second. Stephen, yes.
It's because we have an explanation of strings, because within code words, there would be a ridiculously large number of strings to go through. that each string is decipherable.
I couldn't hear any of that, but I think what you said is that that's not possible because there's an infinite number of messages, right? So that would be conceptually saying, oh, the answer is to enumerate this infinite set and then look at each of the elements, and that's clearly not what we want. It's not even finite. The algorithm isn't even guaranteed to terminate because you have an infinite number of messages that you can create. There's no bound on the length of the messages. Okay, so again, Stephen, what problem does that remind you of? Well, that's definitely a trick question. I only asked you that because you came in and talked to me a little bit about undecidable questions, but you may not. There's a famous undecidable question. How many people here have taken CS 120? Okay, so does this question remind you of anything? Paul? The what?
Everything we've done, like the state machine.
Every question in 120. Okay, there's one question called post-correspondence problem. Maybe you didn't see it. I won't go into it. But undecidable, oh yeah. You got a question?
So is it Turing undecidable?
Turing undecidable is a term for problems that you can prove do not even have an algorithm that can solve them, regardless of how much time it takes. It doesn't have a finite time algorithm to solve it. And there are problems that you learn about in CS 120 that are undecidable, Turing undecidable, and this problem smells a lot like some of those problems, and particularly the one that's called the post-correspondence problem is the closest. So when I first looked at this, heard about this problem, I said, well, that's probably undecidable, like lots of questions are, because it's, well, not just because it's about an infinite set of messages, but it just didn't feel like there would be a finite time algorithm to solve this question. But in fact, there is. There's a very efficient algorithm to solve this problem. And in fact, people have conjectured that there's a linear time algorithm for this problem. Linear in the total length of all the code words. And I've spent or wasted a lot of time trying to find a linear time algorithm and failed. So part of what I'm doing here in teaching you about this problem is hopefully infecting somebody who, either at the end of this quarter can solve that problem or 10 years later come back and tell me the answer or something. Okay, so what I want to show you is a efficient algorithm for solving this problem, and the algorithm is based on building a graph, a directed graph, and then looking for particular types of paths in that graph. And we'll prove that if you can't find one of those paths, then the code is uniquely decipherable, and if you can find one of those paths, then it's not uniquely decipherable. Okay, so this is something that really should use an example. These do get a little bit messy, but so here we're going to build. So here's the solution. First thing is to build a graph G from the code and all of its code words. And so when we build a graph, I have to tell you what are the nodes and what are the edges. Okay. There's one node in G for each suffix of a code word, of any code word. Okay? Now a suffix is just a part of the string that comes at the end. So if we take the code word ABA, it has a suffix A, it has a suffix BA, and it has the trivial suffix of ABA. So the code word itself can be considered as a suffix. Right? We're going to have one node for each suffix of any code word. Now, you could have the same suffix appear in two different code words. So for example, the suffix BA occurs here and occurs here. The suffix A occurs in this one, it's 3 times. Okay, but we're only going to have one node for each suffix, not for each suffix and the code word it comes from, just one node for each suffix that appears in any of the code words. Okay, so for example, let's say these are the code words ABA, BBA, BAAA. Okay, let's take that as the code. So these are the code words. So these are the trivial suffixes because they consist of the code words themselves. And then what are the suffixes? Well, obviously there's a B, there's a code word, there's a suffix B, but I better make my example the same way I have it on the paper, otherwise I'm going to get confused. There's a suffix A, there's a suffix B, there's a suffix BA, there's a suffix AA, and there's a suffix AAA. Are there any other suffixes that I've missed? So we have the trivial suffixes here, and then we have the non-trivial suffixes here, the ones that really exist. Okay, so this set of code words is not the same as this example over here, right? It's a different example. All right, so that's the node set of this graph that we're going to build. And then we're going to put in some edges under 2 different rules. Okay. There is a directed edge from the node for suffix U to the node for suffix V. Okay, so U and V, these are variables now that represent suffixes. It's not literally the suffix of just a single character U and not literally the suffix of the single character V. These are designating, these are variables that represent suffixes. If one of 2 things happens, there is a code word C equals UV, or 2, there is a code word C where U equals CV. Okay, so first of all, let me just say this small c represents a code word. When I'm talking about the whole code itself, that's written by a big C. Okay, so let me just big C so that we don't confuse an individual code word from the whole code itself. Okay. Now these rules are, we need some examples before you're going to be able to internalize what this means. Okay. So I'll do examples, don't worry. But this is called a type 1 rule, and this is called a type 2 rule. So let's see if we can find some type 1 rules. So we're looking for a code word which is equal to one of the suffixes that have been enumerated, followed by a second suffix that's been enumerated. So, for example, AB is a code word. And A is a suffix and B is a suffix. Okay? So if we take C to be AB, then we can take U to be A and V to be B. Right? So there's a code word C, which is equal to U, followed by V, where U is a suffix and V is a suffix of some code words. The U is a suffix of a code word, V is a suffix of a code word. So here's an example, AB, U is a suffix of a code word, it's there, B is a suffix of a code word, it's there. Okay, so what edge should we put into this graph? Yeah.
Is there an edge between A and B?
Yeah, between A and B or from
From A to B.
From A to B, yeah. It's like that, okay? And I could note also, if I want to, that this is a type 1. It's a type 1 edge, and what C is AB. Although that's implied, because if you want to know what the code word is, you just take this followed by that. Okay, so it's really enough to say that that's a type 1. That's a type 1 edge. Okay? Let's look at another type 1 edge. How about from AB to A? Is that a type 1 edge? Well, remember what type 1 says. There should be a code word which is this suffix followed by this suffix. So we're looking for a code word which is ABA. And we have that. That's right there. Okay? So this is a type 1 edge also. And what about, well, let me just, what about B to BA? B to BA. Oh, yeah, right. What about this? Is this a type 1 edge? Yeah, because this is asking, there should be a type 1 edge here if there's a code word which is B followed by BA. And there it is, BBA. Okay? So that's a type 1. And my example isn't quite complete here. This one, what about this? A to AAA. No, because that would mean there'd have to be a code word A with 4 A's, at least under type 1 rules. We haven't looked really closely at type 2 yet. But there should be one from A to AA, right? Because of this one. And we can put in some more, a lot more edges. Now let's look at type 2. Okay, this one, type 2, maybe is a little bit harder to get your head wrapped around. There should be an edge from U to V if it happens that U is equal to C followed by V, where C is a code word. Yeah? Oh, I know why. Because I messed up. Yeah, because when I was looking at this, I was seeing AAA. It's B AAA. And that explains why it wasn't on my paper either. When I was looking at the paper, I was thinking, uh-oh, I screwed up. And in fact, I did, but not then. Not when I wrote it. Yeah, good.
Try BA.
So, yeah, so let's just BA to AA is what I have written on the paper. Okay, and that's right, BA, AA. So BA and B and AAA, and that's that. So this B is all the way over there. Okay. Yeah, good. Okay, back to type 2. There's a code word C where some suffix u is equal to the code word followed by another suffix v. Oh, question?
Yeah, this kind of is sidetracking, but why can't we just have a finite state machine and keep track of like the non-deterministic, like the different choices you have, and after you run it once, remove a choice, and if you still have another choice, it means there's two options.
It sounds like what you're proposing is a way of taking a specific message and determining whether that message is uniquely decipherable. For the problem statement, we don't have messages. The problem statement is just given the code, and then, yeah.
Could we also do B and then A?
Yes, I haven't finished all of this. It gets kind of cluttered, but yeah, definitely there's a B to AAA, because B AAA is a code word, and that's also a type 1. So yeah, you can try to look for all of the type 1. I think we're actually just missing this one, which is the ABA. That's a type 1, and this is 1, and this is 1, and this is 1. So if I did this right, I think these are all the type 1 rules. Okay? All right, so let's go on to type 2. Type 2 rules is, again, that we're looking for two suffixes, u to v, where u is equal to a code word followed by another suffix. So, for example, this one, if we have u is going to be ABA, and we're going to have C equal AB, and and V is A. So does that fit this rule? So ABA, which is a suffix, it's a trivial suffix, but it is a suffix, is equal to C, which is a code word, AB, followed by another suffix, which is A. So it looks like that's a type 2 rule. Okay? Does anybody see any other type 1s or type 2s? Yeah.
That's a question. What's the difference between a code word and a suffix again?
Okay, a suffix is the substring that occurs at the end of a string. Any one of the suffixes, any one of the substrings that occurs at the end of a string is called a suffix. Okay, so if this is a code word, the code words are the strings that are actually in the code, and the suffixes of code words are all the strings that occur at the ends of the code words, including the trivial suffix, which is the entire code word itself. Okay, so it's any substring that runs all the way to the end of a code word is a suffix. So here we've enumerated, for this set of code words, these are the trivial suffixes also, and these are the non-trivial suffixes. Okay, anybody see any other edges that should be in this graph, type 1 or type 2? Yeah.
BBA to BA.
BBA to BA, and the reason is, that's a type 1 or type 2?
Oh, wait, B is not a code word. Never mind.
It's a what?
Oh, B is not a code word. So never mind.
You're retracting this?
Yeah.
Okay. I think this is all of them, but I could certainly be wrong. Okay, so all we've said so far is, this is in the solution, you build this graph. And this is clearly something that's efficient to do. We could do a running time analysis of it, but it's not a big deal to enumerate all the suffixes and build this graph, look for the rules. It's certainly within polynomial time. It's certainly within something, well, at any rate, we'll get to the time analysis in a bit, but it certainly doesn't look horribly inefficient exponential time to build this graph. Okay, then I'll give you the theorem, which will then have to try to justify. Theorem. C is not uniquely decipherable if and only if there is a directed path in G from a node representing a code word if there's a path, well, of length GTH, length greater than 0, representing a code word to a node representing a code word. Okay, so in these nodes in the graph, some of the nodes are representing code words. Those are the ones that are here in this example, and some of them are representing suffixes that are not code words. Now, in this graph, do we see a directed path from a node representing a code word to a node representing a code word? I put in the extra condition that has to be greater than 0, otherwise you might just say, well, a path is from a node to itself trivially of length 0, but that's not of interest. We mean a path that really goes out somewhere and then comes back. Now, it doesn't have to come back to the same code word, although it's permitted to. So the path can go from any code word to any other code word, even itself. But in this particular example, there is no directed path from a node that represents a code word to any other node that represents a code word, including itself. There is an undirected path, but that's not of interest. Okay. So according to the theorem, this set of code words, this code is uniquely decipherable. Any message that you create by concatenating these code words, even with repetitions, even with unbounded length, that every message that you create that way will be uniquely decipherable. There's only a single possible parse to parse that message. On the other hand, if we now add in, let's say we add in a new code word here, another code word, so BABB, oh, actually, I don't know. I said on the other hand, and that's not true. I don't know yet. BABB. So why did I pick this one? Just because it generates some more interesting type 2 edges. And I wanted to give an example of some type 2 edges. So if I have BABB, now what additional edges do we have? Okay. Well, according to my notes, we have ABB to B. ABB. Where's an ABB? Oh, we have some new suffixes now too, right? That's a new suffix because it comes from there. All right. And we have a new suffix which is BB also. So B we already had, BB, ABB, and then BABB. Okay. And now we have ABB goes to B, ABB goes to B, and why is that?
Because BABB.
Yeah, because you have BABB, which is a suffix, is equal to is equal to, we want it to be type 2, so this should be a code word. This suffix BABB is equal to code word AB followed, yeah. I reached my limit on how much examples I can, after a certain, there's like, they say in psychology you can remember 7 things at once, and then after that your brain is fried. There's a limit on how much of an example I can actually work through before I just get totally confused. But okay, so this wasn't going to be an example necessarily of one that does have a directed cycle. Let's look at one that we know is not uniquely decipherable and see how it has a cycle. Or actually, that one. This is so trivial. ABA. I erased that code already that was used for here, but it had definitely an AB in it, and it had an A in it, and we can see it right here. And it had an ABB, and it had a BA and an AB. Okay. So, and then the suffixes that are not here is just B, BB. Anything else? So it looks like, for this example, we have the nodes representing code words, and then we have the suffixes that are not themselves code words. And then we have the type 1 and type 2 edges that should be there. And we've already seen that this is just, even the message ABA is not uniquely decipherable because you can write it as a single code word, or you can write it as AB followed by A. All right, so we should have edges in this graph that form some directed cycle according to the theorem. Okay, yeah.
Your top code word should be ABA.
It's what?
Your top code word should be ABA.
Oh, ABA? Okay. Well, where's the cycle? Somebody help me out here. Otherwise, I'm going to have to try to think in real time. It's what?
ABB to BB.
ABB to where?
BB.
Okay.
A is a code word, BB is a suffix, and ABB is a suffix.
Right. So is this type 1 or type 2? It's what? 1 or 2? 2. Okay. What else?
A to BA, type 1.
A to BA, type 1. Okay, yeah.
Isn't that all we need, though?
Isn't that a requirement? Directed path from one code word to another.
Oh, okay. Yeah, good. Right. I was thinking of it as a cycle, but it doesn't have to be a cycle, a path. Yeah. Okay, from A to BA, there's a directed path from one code word to another code word. All right, so we've proven this theorem by example. We've had 2 examples, and they both satisfied the theorem, and so that's all you ever have to do to prove a theorem. All right, so let's try to prove the theorem. And I'm not going to get through it today, but the proof is essentially constructive. That is, when we assume that the code is not uniquely decipherable, we'll have 2 messages. We'll have one message with 2 different parses. And we'll use those parses to actually create a path in the graph that goes from a code word, a directed path, from a code word to some code word. And then we'll think of it conversely. If you have such a path from a code word to another code word, that should tell you how to generate a single message that has 2 different parses. Okay, so do one direction. and I won't even finish that today, unfortunately. Okay, so the proof of the theorem, we'll do it the direction, assume that C, the code, is not uniquely decipherable. So that means there's some message that has two different parses. Okay? There's some message, and that message, call it M, is built from the code words of C. There's some message M that has two different parses. Okay? So just pictorially, this is going to be a kind of a representation that will be useful. That M starts with one code word in one of the parses. So this is a code word followed by another code word, followed by another code word, and so on. So there's little gaps in here, but think of them as all being concatenated. That's so your eye can see it. So this is a parse that has 1, 2, 3, 4, 5 code words, the top one. And the bottom one has 1, 2, 3, 4, 5, 6. Just to be sure you're clear that you don't have to have the same number. Okay? But they both start and they both end at the same place, so they're both spelling out M. There are two different parses of M, which is why this message is not uniquely decipherable. Okay? Among all such M, consider the shortest one. Okay, so there may be, if the code is not uniquely decipherable, there may be many messages that are not uniquely decipherable, and all we need is one in the argument, and we're going to take the shortest one. That's going to simplify. A lot of times in proofs, taking an extreme case, the shortest, the longest, whatever, helps in constructing the proof. So here we're going to take the shortest such code word, the shortest such message. Okay. Then we're going to let in this proof, we're going to let C1 and C1 prime these are the first code words in the two different parses. First code words in the two different parses of M. Okay? So in this proof, we're assuming first that we have the short, we're assuming there's a counterexample. There's an example that shows that the code is not uniquely decipherable. We're looking at the shortest of such examples. And our first observation, well, we call C1 the first code word of one of the parses and C1 prime the first code word of the other one. And our first observation, observe, the length of C1 is not equal to the length of C1 prime. Why is this? Yeah.
If they were the same length, they'd have to be the same word, and then they wouldn't be the shortest. Yeah, they wouldn't, if they were the same, yeah, if they're the same length, they're the same code word. And then you'd have a shorter word that has two different parses.
Right. Yeah. So let me say this again. Let me say this. If these were both the same length, well, we know that they're both equal to the beginning of M. Here's the parse of M. So if they're both the same length and they're both equal to the beginning of M, they're equal to each other. Okay? So this would be saying that they're starting out with the same code word. These two parses are starting out with the same code word. Yet we know the two parses are ultimately different. Okay? So, and end up at the same place. So if they both started with the same code word, why don't we just consider this as a new message? This is a message with two parses also, and it's shorter than M, and yet we said that M was the shortest, the message with the shortest message with two parses. So it can't be that the two parses begin with the same code word, and therefore it has to be that the two first code words are different length. Okay. And therefore, I'll just make one last statement and then I'll quit for the day. Therefore, at the very beginning, when we look at the two parses, we look at the first two code words that are here. Not the first two code words, but the two first code words. One is the long one, and one is the short one. So unambiguously, there's got to be one that's longer than the other. And there's also one that is the overhang. So this piece of it is the overhang. And this piece, this substring consisting of the overhang, is a suffix of a code word, namely this code word. Okay, so next time we'll build up the proof and finally give the proof and finish the topic. Okay, so